Okay, thanks, Heather. I just wanted to make one quick comment in relation to the lateral fluxes session that we just finished. There's a group of us who have been pulling together a network to do some synthesis and also methods, discussions, et cetera, on tidal exchanges between wetlands and estuaries. And if you're not in that group yet and you'd like to be, please just send any of the organizers of this session an email and we'll get you looped in. So we're going to have 3 lightning talks now about internal cycling processes, carbon cycling processes within salt marshes. And our first speaker is Iris Anderson.
Thanks, Kevin. So I'm going to be talking about the research we've been doing on 2 Spartina alterniflora marshes in North Carolina. And the work was done as part of the Defense Coastal Estuarine Research Program, which is a DoD program. Now, I said we, but really the work was all done by Ken Zappala, and he has a poster this afternoon, and I encourage you to go and look at it. And we had lots of help from Ellen Herbert as well. So we asked 3 questions. How does fertilization, location of the marsh in the landscape, and hydro period affect first the pool water chemistry, and secondly, the trophic status of the marsh? Secondly, we wanted to quantify the net exchanges of carbon between the marsh, the atmosphere, the adjacent creek, and the sediments. And finally, we scaled up first on an annual basis per meter square, and secondly, on an annual basis for the whole marsh. Okay, so we had two marshes that I mentioned. One right here we'll call Freeman Creek. Creek discharges to the Intracoastal Waterway. This is the New River Estuary surrounded by Camp Lejeune. This is our second marsh, Traps. And the 2 marshes differed by a lot. Freeman had about twice the tidal range of Traps. Secondly, sediment input. Freeman also had about twice as much sediment, organic carbon input as Traps. And then inundation time. Freeman's sites were rarely inundated. Well, they were inundated, otherwise we couldn't make measurements, but they were inundated for a much shorter period of time than Traps. And so here's some of our pool water data. And so, I should have mentioned, we had 6 plots on the edge of the marsh, 6 plots in the interior of Freeman's, and then at Traps we had 6 plots on the interior because we're interested in location. And so here are some of our pool water data. And these are all Freeman Creek. You can see the edge did not accumulate much in the way of ammonium. In the interior, a little bit more, and at Traps, a lot more. Sulfide pretty much followed the same pattern with very little accumulation on the edge. And then trophic status. So everything above the x-axis represent a net heterotrophic marsh. Everything below is net autotrophic. So Freeman's Creek was all net heterotrophic. Traps was net autotrophic. Fertilization increased heterotrophy on the edge and in the interior with a bigger effect on the edge. And in the interior, I thought it was interesting that fertilization decreased net autotrophy. Okay, these next bunch of slides show losses and gains with all losses above the x-axis. So metabolically, Freeman Creek lost a lot of carbon and Traps accumulated a little bit of carbon. But then we also looked at lateral carbon export. We measured DIC plus DOC in groundwater wells, and we also had discharge rates, and so we scaled that up to the whole estuary. And then we also measured DIC plus DOC in overlying water, assuming that all that water would drain off and contribute the DIC plus DOC to the creek. And we were disappointed, these little red bars represent lateral export from that marsh. Not a big number compared to the other sources of carbon. Okay, and then we added to that sediment organic carbon input, and this was based on Marker Horizon data. So you can see that in the interior of Freeman, there was a lot of sediment organic carbon input, as well as Traps. but along the edge, this little blue bar shows us that at Freeman, on the berm, on the edge of the marsh, there was very little sediment organic carbon input. Then we added it all up, so the yellow bars represent the total. And so at the interior marshes, both Freeman and Traps, there was net accumulation of carbon. At Freeman's on the edge, there was not. There was net loss of carbon. And then we scaled up to the entire marsh. And so you can see the whole marsh as a whole does accumulate carbon. And most of that carbon is coming from organic carbon deposition in the sediment. A little bit of export, this is CO2, net CO2 loss. So the take-home message, I have 2 seconds for all of this, is if you have a net heterotrophic marsh, you need to get and have enough sediment organic carbon input to maintain that marsh and to let it accumulate carbon. Thank you.
Thanks, Harry. That was great.